Okay, and example 7, we're going to have a special case here. We have a choice in terms of what method we want to use. In this case, I'm going to use substitution, and again, the variable that I will solve for will be x in that first equation because the coefficient of it is 1, which makes the substitution a little easier. So if I solve for x here, I would move the negative 2y over, so I'll end up with x equals 2y plus 3. So we're going to take that 2y plus 3, and again, the second part of substitution, we solved and we substitute. So we'll plug 2y plus 3 in for x. So it's just a straight substitution there. That will give us this, replacing, again, this x with 2y plus 3. As we work our way through this one, what we'll notice is we end up getting something kind of funky. All right, as we distribute this through, we get to our second portion there, and the 4y's end up canceling. The negative 4y and the positive 4y cancel out, leaving us with negative 6 equals 1. All right. Last time I checked, negative 6 does not equal 1, so this is not a true statement. So what this tells us is that there is no solution. This is an inconsistent system, and if you were to graph both of these, they would be parallel. All right. So when lines are parallel like this, they do have the same slope, okay, but a different y-intercept, okay? So that's the case which will happen when you have parallel lines. They'll never intersect, and for that to happen, the slopes would be the same, but the y-intercepts would be different. You could verify that by putting both equations in slope-intercept form, or you could use standard form shortcuts of slope equaling negative a over b and the y-intercept equaling c over b. Okay, so that is an inconsistent example. All right, this next one, you can see it just says solve algebraically, so you have a choice. In this case, I'm going to use elimination. All right, so if I'm going to do this, I look at this and I notice that the x's, we have 2x and 4x, so both are positive. For the y's, we got negative y and negative 2y, so the signs are the same. I know with elimination, I want the signs to be opposite, so I'm going to have to take that into account here. So if I wanted to eliminate the x's, I got 2x and 4x. My thought process is I could make this 2x become negative 4x pretty easily by multiplying the entire equation through by negative 2. So if I do that, that becomes negative 4x plus 2y equals negative 2. And then that bottom equation, I'm just going to recopy, so that's 4x minus 2y equals 2. If we combine those together, what we'll notice is everything drops out. So we end up with 0 equals 0. All right. So this is a true statement. 0 does equal 0, which tells us that these two equations are actually the same line. All right, so if you were to graph these, it would just look like it's one line, and they would be overlapping at an infinite amount of points. So we say oftentimes back in Algebra 1, you said that there were an infinitely many number of solutions, which is okay, but that, again, gives us a false sense of representation sometimes, thinking that any point would work, and that's not true. It's any point that exists on the line. So what we can do to be a little bit more specific is to let x equal a. All right, so if I let x equal a, what that will allow me to do is now solve for y, and you can pick either one of the equations. So if I pick the top one, 2x minus y equals 1, now I can get a representation of what y would be in terms of a. So I'm just going to take that a and plug it in. And when I do that and solve for y, I'm going to end up with 2a minus y equals 1, or negative y equals negative 2a plus 1. And then we would divide by negative 1 to get y equals 2a minus 1. Okay, so that would be our general solution for this system. So what that means is, like, I can plug in a value for a, so like a was 5. I can now take that 5 and plug it in to this part, and then 2 times 5 minus 1 is 9. So that lets me know that the point 59 is on the left. All right, so it's just a little bit more specific way for us to represent an infinitely many solution. Okay. The next part, I just want to talk about a couple things. Here we have some decimals involved, all right, and you can deal with the decimals if you want. However, we easiest to get rid of them if you can, and you'll notice within all of these values, we go 2 places past the decimal. All right, so to get this to the integer values, you can multiply this equation through by 100, and then this equation through by 100, and that will get each decimal to move over 2 spots. So if we rewrote that, we would look at something like this. All right, this system right here would be one that I would not utilize substitution for if I had a choice, because none of the coefficients in front of the variables are 1 or -1. So I would probably utilize elimination. I would probably choose to eliminate y because the signs within those terms are opposite. So if I look at -5 and +4, the least common multiple between those are 20. So I can multiply this equation through by 4 and this equation through by 5. And that will then allow me to solve that system. Right? I'll have the y's will end up eliminating, and then we can work from there. I'm not going to do that, but I just wanted to showcase how you can handle those decimals. All right. One other thing that is not on your notes that I want to address is, what if you have fractions that you got to deal with? Okay. You can deal with the fractions accordingly, but if this was one equation that's part of the system, most people would want to get rid of the fractions, and that's what I would probably do. So if this is like the first equation that you're dealing with, what you need to do is find the least common multiple, or just the common multiple between 5, 8, and 2. All right. If I'm dealing with that largest value, 8, okay, and I think about I got to compare that with 5, I know 5 multiples of 5 are 5, 10, 15, 20, etc. And multiples of 8, 8, 16, etc. But the ones with 5 end in either 5 or 0. All right, and the next multiple of 8 that ends in 5 or 0 is 40. All right, which is also a multiple of 2. So what I'm getting at here is we can multiply this through by 40, and now we'll have a friendlier equation to deal with. Okay, and then we can combine that with whatever other equation we need to deal with in order to finish off the system. So you may see some like that. If you got fractions, find the least common multiple and get rid of them. That concludes the videos for section 3.1. We will address word problems in our next meeting.